Okay, thank you for this introduction. I am Tomasz Żyjewski. This is, I believe, my third time on the Yocto Summit. The topic of this presentation is enabling the UEFI Secure Boot on the x86 platform with Yocto, which more or less is just getting started with the Meta Secure Core layer, which can be found on GitHub. Okay, so let's start with the agenda for this presentation. First, I would like to introduce myself and the company I work in. Next, I am going to talk a little about the security in the embedded device world. I'll try to explain which sections should be considered to provide a secure solution to our clients. Then I briefly discuss the process of booting the embedded devices in case of the x86 platforms, and narrow down the subsequent phases of starting the platform, just to mention where in the whole boot process we can fit the UEFI Secure Boot functionality. So the previous slides will introduce us to the main part of this presentation, so the UEFI Secure Boot. After 2 or 3 slides in which I'll try to explain what it is, what is the goal of the UEFI Secure Boot, and provide a description of some UEFI variables. We'll get into the Meta Secure Core Yocto layer, which provides this functionality of the UEFI Secure Boot to the Yocto project community. After the overview, we'll go through the scenario that I came up with to test the discussed layer, and the presentation finished with me discussing the results and providing the summary. That's me, and here's something about me. I am an embedded system engineer at FreeNDEP. I am working here for over like 3 years now, during which I gained knowledge related to Yocto. I have quite a lot of experience in integrating update system, mostly based on the SW update from the Meta SW update. And I also enjoy working on updating the Yocto layers, which is always a demanding tasks, especially when the customer asks for an update after several years of using the system. And in my spare time, I try to find Yocto layers that seem to provide interesting functionalities and later test them. If you would like to contact me, you can use an email list here or just hit me on Twitter, at least, if it will be still up. Okay. Now, I would like also to introduce the company I come from. FreeNDEP is an embedded system consulting company. We are based in Gdańsk, which is in Poland. One of our main goals is to promote open source solutions by using them on the firmware and systems we work on. We just strongly believe that following the path of open source increases the security of the devices around us in today's world, and thus also our security. Okay, so let's go through the subject, and let's start by me trying to explain what embedded system security is. I think that using several definitions and combining them and drawing certain conclusions from assimilating them, we can just conclude that this is a methodology for designing and implementing embedded solutions, just that are emphasizing limiting the possibility of encountering a threat. And that given threat, of course, is an unauthorized action performed using our device, the device that we prepare system or application for. At this stage, I believe it is worth assimilating a few terms that we will use or should use when designing the target solution. So a couple of security terms. Terminology. The attacker can say that it is an individual which is performing a malicious act in the real time. A threat actor, which is a source could be a software, could be a person, which with a malicious intent. Next, we have the vulnerability, which we can call a weakness that that will be exploited by the threat actor to perform a dangerous act with our operating system or program. Then we have the attack vector, which is the path chosen by the threat actor to attack our vulnerability. In the case of embedded devices, it can be, for example, an internet connection, because today a huge number of every kind of device is connected to the internet, to the network, or it could be something that are on our board, like the flash storage, or I know the SPI lines, etc. Next, there is an attack surface, which is the target of the attack. The element that the threat actor wants to affect can be, for example, some user application. Okay, so now let's think about when we call a device, when we call the device secure one. We should consider the above mentioned terms and just list all the known attack vectors and surfaces that can be used on our device with our solution. Then take as many steps as there will be needed to implement our target solution in such a way to prevent the use of those attack vectors. So yeah, there's a lot of trust in the embedded system industry that companies implement and follow the latest standards for security and functionality requirements. And when we talk about the security of embedded systems, I believe you can divide the consideration to the following sections. There is development environment security, the hardware security, operation system security, the application, and the data transmission security. I will go quickly through all of them. So first, the software development infrastructure, where the code is generated, tested, compiled, etc. Just requires security safeguards to ensure that there is no room for internal or external malicious actors, because we just can't provide secure solution by working on it in a non-secure environment. Next, we also need to consider whether the device to which we deliver our solution is trustworthy. Here we can think about interfaces exposed on the board, let's say, such as the Ethernet ports, the debug words, the JTAGs, but of course we can think about some protection, software protection for that, so to secure our, for example, JTAG inputs. Because all of these interfaces may be an attack vector for some unauthorized users. We also must not forget about the housing of the device, whether it is secured or whether the board is whether the platform inside provides, for example, some anti-tamper mechanism. So those are the things that we can think about when talking about securing our hardware. Next, we have the operating system area. We can think about the securing login access here, for example, whether directly or via the SSH connection. We should also consider the ports that are open, if all of them should be open or not, or about the user's permissions to given files, for example, by integrating in our system the Linux policies. And think about hardening the Linux kernel itself by just using the appropriate configuration. In this area, we should also mention everything that runs on the device before the OS starts. So also consider the whole boot process, consider whether there are any areas that the threat actor can use. Next, we have the application area and what we can do to secure it. Technically, we can just think about the quality of the code that we run on our device. There should be no memory leaking. We should prevent the use of given application for the negative operation of the entire system. So application should have access only to the resources that it really needs, not the whole operating system. Yeah, later the last area mentioned here is the globally data transmission process. Here we can just deal with the exchange data between applications, maybe using some protocols like SPI or A2C, or maybe between the edge device and the gateway with some technologies like Bluetooth Low Energy or the Wi-Fi, or between the gateway and the cloud. So yeah, as you can see, ensuring that the device is considered secure is a big task, and probably separate teams should work on every of the relevant area, just to make sure that everything is secured. The middle area here is highlighted in red because it is the one of one of its subparts that we deal with when talking about the UEFI Secure Boot, because this is a part of the booting the device, booting our operating system. Okay, so a little disclaimer before we proceed. I want to point out that the subject of UEFI Secure Boot is really complex and multi-layered. With a pinch of salt, what I will present in theory covers less than 1% of the knowledge needed to understand everything here. However, I decided that a few basics would be needed to understand the elements necessary to integrate UEFI Secure Boot in Yocto projects. It is also worth acquiring knowledge from the topics listed here to understand the subject better. Maybe one good resource to get this knowledge is to take the Open Secure Training 2 course, which covers UEFI Secure Boot in one of its lessons. And the link for those two, it is displayed here on this slide. So yeah, let's maybe continue with a little parable that was used in the UEFI Chain of Trust white paper to describe the securing the device, the system. Let's imagine a multi-million-dollar estate with high walls and a moat around it. And let's say they are packed with monitoring, some automatic alarms, drones tracking all activity, etc. Each of these examples could be assigned to a separate security area, just like those I described in the couple of slides before. To us to feel safe in this kind of mentions, each of those elements must work well and just protect us from the danger from the outside world. What's more, each of the defense elements in some way also depends on the previous segment. Let's say, for example, it is harder to overcome a high wall when there is a moat under it. So now let's imagine a tunnel running under all this construction that leads us straight to the danger. That means that every of the components that we just said, that those cameras, those alarms, would probably not work and to not protect us from the danger because we have this tunnel under everything that transfers us. So yeah, let's try to think about this situation just in the world of embedded systems. So in the embedded systems, that tunnel could be assimilated to some faulty firmware that we ask to boot our device. If you do not get rid of this tunnel, any effort put into securing subsequent layers, so I don't know, the kernel, bootloader, system itself, yeah, the whole effort may be lost. For example, by making the faulty firmware run some completely different kernel or something like that. So for this, we need to ensure two things. The first is the fact that subsequent firmware elements do not have attack vectors, and the second is to ensure that no one can interrupt the boot process to upload their firmware. So now we can introduce two more security terms, which are the root of trust and the chain of trust. The root of trust is just the source that we can trust to be secure. So the point here is that the trust state of the given boot element, let's say the bootloader, must be based on something that we have no doubts about. The root of trust itself can be hardware typed, like using the TPM with some key inside, or provided by a previous item from the boot process. So we can say that we can trust that everything before some state of booting is trusted because some previous functionalities give us this information. Next, there is the chain of trust, which is achieved when every previous element verifies each element of the platform's boot process. So to achieve this, many components are used to cover the entire boot process. Example, starting the BIOS bootloader and loading the Linux kernel. In this case, the UEFI Secure Boot uses the certificate stored in the BIOS to verify the part of the whole booting process. Okay, so a couple of information about the Secure Boot. It is defined in the 32 chapter of the UEFI specification, and everything we can find there should be the root of trust of the UEFI Secure Boot. The main task of it is to authorize the system bootloader and the UEFI drivers using the keys that are provided by the platform owner. This is the person that decides which firmware should be run on our platform. Yes, so the UEFI Secure Boot is controlled by the UEFI authentication variables, and they are used to provide the UEFI Secure Boot policy that determine which images and certificates are allowed only and which are not. Okay, when talking about the UEFI Secure Boot, we just need to remember that using just word Secure Boot may means a couple of things. It can be some vendor-specific functionalities that define and verify some early boot phases. Or it just can be the UEFI Secure Boot, which is described in the UEFI specification. So it is it is important to remember that when talking about the UEFI Secure Boot, we need to use the whole phrase. And yeah, from the operating system perspective, we can deal with the UEFI Secure Boot in 3 ways. We can just use it with the preassigned keys, which are provided by our OS, like Ubuntu or something like that. We can just disable it, or we can sign everything with our own keys. So yeah, there are those 2 variables that I talk about, which determine the UEFI Secure Boot policies. So we have the platform key, which is enrolled by the platform owner and saves the public key part on the NVRAM. Private key can be used here to change the platform ownership or enroll key exchange key, and should be protected by the platform owner. The platform key establishes trust relationship between the platform owner and the platform firmware, and it is recommended to use here RSA 2048. Then we have the key exchange key, which determines who is authorized to update the DB and DBX. Its public key is also stored in the NVRAM, and the private key can be used by the operating system or the third-party application to communicate with firmware in trusted manner. So the key exchange key just establish a trust relationship between the operating system and the platform firmware. Also, we have here 2 significant databases, so the DB and DBX. And just the DB database, it's a list of platform-defined allowed lists. So the certificates that are there are allowed to run on our platform, and the DBX define the certificates that are denied. Okay, so Let's now go to the Meta Secure Core overview. The link for the repository is provided on the slide. As you can see, there is one default branch, which is the master branch, and a couple of stale branches like the Rocket and TAD. So you can see that this layer it is with us from a while. Latest changes here we present what the previous month. So yeah, maybe it's not a lot, but say us that something is going on with this layer. So probably it is safe to just test it because someone else also did something with that. Okay, so yeah, the layer just provides us the couple of common and platform-specific security features. It's divided into 9 sublayers. One of each, every one of it has its own README with some more detailed description. One of them is just the core layer of this Meta Secure Core, and is used to provide images that use those functionalities. We'll go through the functionalities in the next slides. There was about 22 issues. One of them mentioned to maybe hosting this layer on the Yocto Project org site. Probably if it would be done, then maybe more people would get interested in this layer and make it more popular and more reliable. Also, there are a couple of more statistics here. So there was 3 open pull requests a couple of days before and over 200 closed. So we can see that it is always updated, this layer. Yes, also in the README, we can see a section that mentions a reference implementation based on this layer. Here is also a link for that, but it was not touched for the 5 or 6 years, at least on the master branch. So it may seem old and maybe not working well. And yeah, also the whole project just looks like it lacks some easy getting started documentation or information how to integrate it with our own project. So yeah, those functionalities that are provided in this layer are the UEFI Secure Boot and the Mock Secure Boot. Mock Secure Boot is the functionality that expands the usability of the Secure Boot, which use some additional shim loader to increase the security of our platform. There is the key store sublayer, which provides us with some development keys that can be used for UEFI Mock Secure Boot. We'll use it in our scenario. There are 2 TPM layers, which give us some drivers for the TPM in version 2.0 and 1x. Next, there is a layer for encrypted storage, which give us 2 types of granularity for storage encryption. So we can encrypt some data volume with the password given by user within the system, or encrypt the whole root file system partition except the boot partition. There are also the MEI sublayer, which introduces hooks within the Linux kernel to support measuring the integrity of files that are loaded before they are executed. The mod sign, which provides us a possibility to sign and verify the kernel modules that can be loaded, and the RPM signing sublayers, which provide the integrity verification for the RPM package. Yes, later, there is the Secure Boot sublayer, which we'll use in our scenario. It provides the extensive description for the README and provides both the Secure Boot and Mock Secure Boot, UEFI Secure Boot and Mock Secure Boot functionalities. It uses the keys from the meta signing key, because they provide the PK, KEK, DB, and DBX key that I explained in previous slides. There's also a helpful quick start for the fixed boot section that we'll use in our POC, and I will describe it later. Okay, so here's some Yocto metadata inside this layer. We will not use the C loader and the shim ones because those are for the mock secure boot. Yeah, there are some include files from the grub to assign needed components, let the grub itself, and also there is the mock.util utility, which allow us to talk with the certificates from within our operating system. Okay, so quick see to the layer conf file inside the Meta Secure Core. From it, we can see that this layer depends on the core and open embedded layer, which are the from the POCI Meta Open Embedded. There is also parallel layer, which can be found in Meta Open Embedded, and Secure Core and signing key layers, which are from the Meta Secure Core layer itself. We can also see here that this layer is compatible with the Hoinster on N Langdale versions of Yocto, so really up to date. Okay, there is also one important thing. So there is the FE tools recipe, which prepare us the lockdown FE executable. This is the executable that is started on the first boot of our after the system run, which enroll the certificates to our BIOS, and then it is later used to verify the grub and kernel assigned by us. Okay, so for test, we'll use our Meta TTS repository. This is a repository that provides a set of tools running in minimal Linux environment to deploy, update, and maintaining firmware on the Shiro supported devices. The Shiro is just an core boot based firmware that we provide to our clients. Yeah, this layer consists of some patched tools like the Flashroom and FW update. It provides sets of core boot utilities from the core boot repository like CBMM and CBFS tool. It's bootable via the USB and iPXE on the page we store here, and the communication can be found on the docs-r.com. For this scenario, we'll use the USB booted image. The image recipe can be found in this path. It just installs some utilities and provides auto login. To create this image, we use the vids utility, and the WKS file can be found in this path, and it looks like follow. You can see that for boot partition, it uses the boot emg BIOS plus FE plugin from the POCI repository, and the effort that I need to do for this POC can be found in the pull request I mentioned here in the slide. Okay, we'll test on the real hardware. This is some Nova custom laptop with the Dasher deployed and the Secure Boot enabled. With some default key, which we'll need to remove and later enroll our certificates on the Meta Secure Core. So yeah, assumptions here will be that to boot via the USB and integrate as much as possible to our Meta DTS. So not use the image just from the Meta Secure Core to test if integration can be flawless. We'll only use the UEFI Secure Boot without the mock Secure Boot. So we'll need to unset the UEFI loader variable. To verify, the verification will be just to try to boot our system, sign it with the keys from the Meta Secure Core, and not be able to boot any other system, like, for example, the Ubuntu. Okay, so to prepare the image for the UEFI Secure Boot, we'll check the example provided in the Meta Secure Core repository. You can see that it uses the Secure Core image init.mfs and install just the package group FE Secure Boot. So we just do that, create the image, which use the init.mfs and install the package group. We're not using the UEFI loader, so we set UEFI loader to 0 in distro configuration file, and also set a couple of distro configuration as it is set in README of the Meta Secure Core documentation. For now, compiling should be just straightforward, but we get some build errors. The Linux Yocto could not do the do sign function. So it looks like the signed image cannot be found. And this I expect is to put it into the boot partition. So we did a little investigations, and it turns out that when we set the C loader to 0, that makes the UKSBL sign function that should sign our kernel just do nothing. And turns out that there is another variable that needs to be set, which is the grab sign verify. And after we do that, we just successfully provide our image, which was the bits GZ image. We flashed it on the USB stick, and wanted to go further with the instructions that were added in the README of Meta's UEFI Secure Boot. So we should deploy the root file system, which we already done on our USB stick, then power the system and remove the enrolled certificates. It can be done in BIOS setup, turn on the secure boot, exit setup, reboot. Then automatically the system should boot using the automatic certificate provision option in the grab boot menu, and boot the system with the protection provided by UEFI Secure Boot. And we think that it can be this easy, and yeah, it wasn't, because it turns out that there was not non-boot option called automatic certificate provision. And we only got the log that system cannot be boot because the signature was wrong. So yeah, turns out that the plugin we used from the Pocky did not depopulate the boot partition that as we would think that it would. So here on the slide is the files that should be on our boot partition, but they were not there. They were only the ones that we built in our DTS system. So for now, we just wanted to check if the secure boot functionality work as it should, and we manually just copy the boot partition on the USB stick. It's maybe because some other variables are not correctly set. We need to investigate that further. So yeah, after we copy by hand the boot partition, there was an automatic certificate provision option which we used to enroll the certificates to our BIOS. But then when we want to once again start the system, the grab was looking for some init ID that we did not provide in our system. So it looks like the kernel command line was just wrong. And yeah, this was some custom one provided by the Meta Secure Core. So we just change it and hardcode the correct kernel command line there, and voila, the system just boots. And we just do some verification. So our system boots. When we try to boot the Ubuntu, it stops on the wrong signatures because we just changed the certificates in the BIOS. We also boot into the DTS and check the states of the secure boot with the mock utility. As you can see here, it says that secure boot is enabled, and we also compare the enrolled certificate with the one generated by the Yocto system. They were matched, so the enrollment was there, okay. And yeah, summary maybe now. We tested the UEFI Secure Boot and looking forward to test the rest of functionalities. Maybe the secure storage will be interesting. And the POC was created with some manual steps, and we still need to make it work automatically. Also, it is worth checking how to use some custom created keys and not the ones provided in the meta signing key. Okay, here are some ways to contact us at 3MDEP. Sorry it took too long. I could maybe prepare better, but yeah, that's it. Thank you for listening.